Yes, this is John Gibbons. I'll be giving an overview and status update of the low-cost personal space weather station, which we've nicknamed the Grape, for the personal weather space weather station project. This is as of September 2020. And for starters, let's take a look at where we're at. Right now, I have in the field approximately 7 of these units collecting data actively. This is what we call the Grape Gen 1. The dotted box is the actual receiver. The internal, external, and antenna input comes in on the left side over here. Comes into a input protection and second order bandpass filter, which you select with a jumper to either be a 2.5, 5, or 10 megahertz. And we feed that signal directly into a SA612 mixer for the low IF mixing. On top here is a GPS amplified antenna going into the Leo Bodnar GPS DO, whose frequency has been set to 1 kilohertz below the selected beacon, so we get a upper sideband frequency of 1 kilohertz. And then the mixer mixes those two signals and spits out a 1 kilohertz signal, which then we bandpass, audio gain it up by 22 dB, do some more filtering on it, and then spit it out to a USB dongle that's plugged into our Raspberry Pi that is running a modified version of FL-Digi, which I modified to accept a 1-second sampling and saving of the frequency estimation for the frequency being received on the audio input from the USB stick. On the end of the day, the 0 UTC, the file gets closed and opens a new one. It also, if gets accidentally shut down, it will keep saving in addition to and adding on to the file rather than deleting it and starting over. This is a schematic of the Gen 1. The antenna input is here. We have a transient voltage suppressor diode here. It clips at plus or minus 5 volts and presents a 2-puff load to the antenna, which is completely swamped out by this 2200 puff right here, so you never see it. I also have a 1K resistor for a DC path to ground, and this is done intentionally to, it slightly widens up the Q, but its main purpose is to bleed off any static charge built up on, if you have just a wire antenna hanging in the tree. Air scrubbing over it will scrub off the electrons and build up a static charge, which will attract lightning. And so for that reason, that's there to help bleed that off and protect the station from attracting lightning hits. We then go into the resonant filter here and you select the inductor set for either 2.5, 5, or 10 megahertz. And then that output feeds directly into the SA612 mixer. The top portion, or the bottom portion here, is the Leo Bodnar input, which we bring in. It's set to an 8 mil current drive. We divide it down here with this 100 ohm, 400 ohm resistor, AC couple it into the mixer, which then mixes the two signals and spits out the 1 kilohertz signal. We then have our high pass filter it here. We have a low pass filter built in here, and we have another high pass filter built in here, which then filters it. We have a gain of 22 dB here, and then that goes through the output to the out connector to the USB dongle, which then goes on the Raspberry Pi, which is then read by FL-Digi running on the Raspberry Pi for the frequency estimation. This here is a picture of the Gen 1 receiver board. It's not very big, as you can probably tell. I think it's roughly, I think I want to say 1 inch by 1.25 inches, 1.5 inches, something like that. But that's a 1N4000 diode, and these are SMA connectors, and these are 0805 resistors, so you get an idea of the scale of it. The antenna signal comes in here. There's the transient voltage suppressor diode there, the 1K loading resistor. This is the LC filter, which then gets coupled into the SA612 mixer, whose local oscillator frequency comes from the Leo Bodnar input jack here. It's divided down with these two resistor AC couple and goes straight into the reference pin. The output of the mixer goes through the filter here. This is the linear audio op amp that gives us the 22 dB gain. We output filter it here and then spit it out here, and this goes to the mic input of a USB dongle that's running on the Raspberry Pi. The picture below is the Leo Bodnar GPS DO that we're using. You program it from the Raspberry Pi, and I have created scripts to be able to set up the frequencies for all of the 7 beacon frequencies we're after, which is WWV 2.5, 5, 10, 15, 20, and 25 if you want. It also does the 3.33, 7.85, and 14.67 megahertz CHU frequencies. So you can actually reference all of those, and the FLDigi auto recognizes the frequency and sets the appropriate label based on the beacon you're listening to at the beginning of the start of each day. This is the Raspberry Pi 4B that we're running the newer ones on. The previous ones are running on 3B with 4 gig of memory, I believe. Or is it, no, the 3B's got 1 gig, and the Raspberry Pi 4B's are 4 gigs, sorry. But one thing I should note is the 4Bs require heat sinking. It's not an option. If you don't, the CPU will throttle itself back during boot. It gets hot that quick. So I've put these copper heat sinks on here, and also you'll notice there's a fan on there that helps keep it down, and we can keep the CPU down to about 40 to 42 C without the fan. If you take the fan out, it gets up to in the upper 50s or the low 60 C. So it does make a significant difference. The lower left corner here is my little 5 volt 3 amp switch mode power supply, which takes its input in from a DC voltage of 9 to 16 volts DC in and creates the 5 volts that runs the Raspberry Pi. I also tap off 12 volts that goes off to the receiver, which then divides it down to 5 volts to run the SA612 and the linear op amp. You can see here, this is the USB dongle for the audio input, and this jack here is running off to run and power the Leo Bodnar GPS-DO. Generation 2 that's on the design board right now is basically Gen 1 on steroids. Each one of these is one of the receiver boards that I was just showing you the schematic for, so we're replicating that 4 times. And we're going to fix the filters on these to 2.5, 5, 10, and 15 megahertz, which will also give us overlap nicely for the 3.33, 7.85, and 14.67 megahertz CHU beacon frequencies. We are intending to create our own GPS-DO. There will be a GPS on board to allow us to get time synchronization accurately, and I'm actually setting the OS up to be a Stratum 1 time reference using the GPS as its standard. So that will be incorporating, it's built into the operating system with a few mods. It's very nice to do, so we'll have an accurate timestamp. We're also planning on using the 1 PPS to, actually it runs the OS 1 second tick input for running the Stratum 1 clock. We're also going to use that for creating the GPS-DO reference, which I'm hoping to get from the clock group, and implementing that on this board to create a reference frequency. That's a TBD that will feed most likely 4 PLL synthesizers. I might be able to double up on these, but they're only 96 cents a piece, so I'm not too worried about if I have to separate them out or not. But that will feed these frequency synthesizers, which then will feed the mixer directly for the mixing for the beacon frequency you're after. We'll have to have an antenna buffer this time because the filters are LCs and they look like a short when they're off frequency, so the other 3 frequencies will be shorting out the one you're looking at, so we need to buffer these and separate them out, which is what this antenna buffer block is for. This is my 5 volt 3 amp switch mode power supply. I'm planning on having a DC wall wart input voltage to it, as well as a separate 12 volt battery backup for power fail retention of the unit, so we don't have to worry about that. And the interface to the Raspberry Pi will have the local temperature sensor, a 4-channel A to D to be able to read these channels at most likely an 8 kilohertz, either a 16 or 24-bit depth A to D sampling. We haven't figured that out yet, or actually I haven't figured that out yet. I haven't figured out where we're going with that. Most likely the A to D will be running on a SPI interface, since we've pretty much used and utilized the I2C bus already. The Raspberry Pi will be running the local temp sensor and the remote interface to the remote temperature sensor and the remote magnetometer for the part of the science experiment, as well as the PLL synthesizers. I believe are an I2C, but they're only getting set when you change frequency, so their bandwidth utilization of the I2C bus will be rather low. So that's basically where we're at. If there's any questions or problems, please contact me, but that should do it.
That was great, John. Thank you very much.
You're welcome.
Yeah. So we do have some questions for you.
Okay, fire away.
All right. So Peter Laws asks, how well will these work in the presence of a 100-watt class amateur HF station?
Depends on how far off the frequency you're operating at. I actually have an HF station at home here. It's a Flex 6500 running 100 watts. And if you're in the same band within the queue of the receiver, it does affect it. But if you're out of the band, it doesn't seem to cause too much trouble. But it's depending on your antenna setup and how close you're transmitting and how close the antennas are. I mean, there's a lot of variables, but chances are it's, like I said, it's going to be on a case-by-case basis, but it can be made to work. But if you're running 40 meters at 7 megahertz and you're listening to CHU on 7.85, you're going to clobber it. So,
but a lot of times, so CHU, those frequencies are very close to the amateur radio bands.
Correct.
Generally. But WWV, they're a little bit farther apart. You're typically listening to like 2.5, 5, 10 megahertz, right?
Correct.
So unless you're operating, say, like 60 meters or you're operating 30 meters, you're probably not going to interfere with this device too much, right?
I have not seen an interference problem, but I haven't been operating a lot either. So, but I'm not expecting a problem.
Right. So I think this is something we're going to keep learning about as we, deploy some of these, more of these prototypes, and we'll want to have people be able to test them in, in a more difficult RF environment. I know Tim Duffy has told us he'd be willing to help us out, so maybe he would put one over at his station during a major contest, and we could see how it performs after K3LR operates one of the major contests. But I think another place we can look for for inspiration on this is, I think another place we can look for an inspiration on this is maybe like people who run RBN nodes, because a lot of those people want to do RBN skimming or spotting so that they can, basically have a spotting network for their home station. And so they've worked out different mechanisms for being able to have their RBN receiver work simultaneously with their HF transmitter. So you might see a scenario where like you either have some sort of interlock between the personal space weather station receive antenna to prevent damage. So if you're transmitting, it would turn off like an amplifier if you had an active antenna. And then we just wouldn't get personal space weather station data during that time. But I think that's fine. I think one of the things we do need to work out throughout this project, and it's going to be a little bit of a process, is figuring out how we really do make these, work within someone's amateur radio station so that, people can feel free that they can operate, the way they want to operate on the amateur radio and still have the PSWS, work at the same time and not have them interfere with each other. And
that's the challenge of a low-cost station, is being able to handle those kinds of overloads and interference at a low cost. So it's kind of a mutually exclusive. I don't have the capability of doing, the roofing filters that the 7851 does for $12,000 a pop.
Right.
I don't have that kind of budget. So
no, and so then that's a good point too, because at that point you say, okay, if you're running the low-cost personal space weather station, these are some of the compromises you might make. And,
right.
And what we would say is, like, if someone's worried about that, you say, okay, well, when you're operating the when you want to go operate DX or talk on HF, maybe it does interfere with the data that the PSWS is collecting a little bit, but that's not a bad thing. We can just, filter that data or not use it. And when you're not, when you're sleeping, when you're not using your ham station, it'll be collecting good data, and that'll be fine.
Yeah. if anybody is interested and we have the time, I've got access to 3 stations running currently, right? Raspberry Pi grapes running at 2.5, 5, and 10 in real time if people are interested in seeing them. But let's answer some more questions first.
Yeah, so I think another question is, and this question keeps coming up, how much antenna will each unit need? So what are you running for antennas right now? Because I know you have about 9 stations, 9 of these low-cost personal space weather stations running right now. What different antennas are you guys using for that?
Right now, my 2.5 and 5 megahertz is running off of a single off-center fed Wyndham, 80-meter Wyndham, which is 135 feet long. It's 30 feet up in the air, so it's horizontally polarized. I'm actually feeding that antenna input into 2 grapes without a buffer, which by my definition should have problems, but it seems to be working just fine. And for my 10 megahertz station, I'm running that off my Gap Titan, which is a vertically polarized antenna. But the intention is to be able to run this off a simple piece of wire strung up in a tree, which the Wyndham pretty much simulates, but it's about a 135-foot piece of wire.
Mm-hmm. I think one of the nice things about focusing on the frequency measurements, measuring varying frequency, is that it really, does not put many restrictions on the type of antenna when you're just measuring narrowband frequency, because we're not worried about, calibrating the amplitude per se. We're not worried about exactly what angle of arrival you're looking at. You're just, all you want to do is make sure that you can receive the signal in question, which is typically WWV or WWVH. So then, you can go from as simple as a random wire that you throw out the window to a K3LR class station. And then you are able to, as long as you can receive the signal with decent quality, you're able to contribute good measurements.
I know that I think it's KB3UMD in Pennsylvania has a wire strung in his basement that he's running his Pi on, and he's doing work. So he's got a little bit more noise on it, but he's picking up the station, which I find kind of amazing. But it's the intent is to make it simple and cheap, because if you're going to have a lot of people doing it, you can't be expecting them to spend thousands of dollars on the expensive tenant system and towers and all that kind of stuff. My intent is you get a cannonball or a tennis ball cannon, you shoot a wire up into a tree, you tie it into the valve, and you're done. So that's the intent of the philosophy of the personal low-cost station.
Yeah, I think that's a really good philosophy, because one of the things I think we're trying to do is we're trying to make these, high quality FMT frequency measurement test type of measurements, which typically it takes a lot of skill. Like we saw Steve Serwin's presentation earlier, where he had these beautiful, spectral displays showing the different modes that are being received. And then we had Dave Kasdan, 88Y's talk, where he was talking about, again, different techniques for both understanding and measuring and understanding the frequency characteristics of the signals you're receiving. And these sorts of things are, it takes a lot of skill to do this, doesn't it?
Yeah.
And essentially what you're doing is you're trying to take those skills and in a way automate it so that we can make those sorts of measurements. We can make it more accessible to people who don't necessarily have that level of skill or equipment, but this would give them the opportunity to make those types of measurements and contribute high quality measurements to the project.
The biggest compromise, or the biggest cost adder that we put in that we found to be essential for making really good measurements, is the GPSDO. That's where we've put a lot of the money into. The receiver itself, the chip is, the receiver and the whole thing is probably less than $10 a parts. Mm-hmm. Getting an accurate frequency standard to make the, the 0.1 or the 0.01 hertz measurements day in and day out is where we need to put the money. So that's
really the heart of this, right?
That's the heart of this whole thing. Yeah. And I'm looking forward to working with John Ackerman about getting his discipline oscillator into my design so we can get a cheap version, because I know we can buy the GPS unit even from Adafruit, has it for like $30.
Right.
and that spits out the one PPS signal, which, to answer another question I saw going by in the chat window, I am bringing the one PPS in on multiple pins, GPIO pins on the Raspberry Pi, because the OS grabs one for the Stratum 1 clock, and I'm bringing a separate one in that I can grab for my data collection engine to know when to take the sample.
Mhm.
So you have access to it. I've actually, on the design, I've actually coming on 3 different pins, and it'll allow you to do whatever you want with the 3rd pin, which will probably be for the magnetometer data too. So there's a lot of stuff going on.
Yeah, there really is a lot going on.
But it's intended to be as flexible as it possibly can.
Yes.
But that's the challenge, is to make
Yes.
something that works really well for really cheap, and usually they're mutually exclusive.
Yeah, it is a real challenge, but I think even the ones that you've developed so far, these initial prototypes, I think we've gotten some very interesting results from them.
Yes, we've learned a lot from the
very
frequency
encouraging.
analysis that Steve did, that having a single top bin frequency estimation works fine during the day, but during the transitions, when we have the ionosphere changing, we need to be able to measure the multiple frequency paths that pop up for a half an hour.
Yeah.
We're working on that. The personal space weather station I'm designing will support any new software that allows you to measure that stuff, because it's really data processing once I've captured the 1 kilohertz tone coming in that you're looking at. So that allows us to have this be a work in progress and still use the existing hardware, both for the station that I have running now and the new one that I have coming out, which will do 4 stations simultaneously. So that's the intent.
Yeah, and it's really important to get that frequency diversity, because not simply because you hear different frequencies at different times of day, which is often true, but it's also incredibly important to get that frequency diversity across CHF band, because those different frequencies are going to be taking different paths through the ionosphere. So for instance, one frequency might be refracting off of the E layer, one might be refracting off of the F layer, and let's say, I've looked at some of Steve Serwin's data, and in one track, you might see traveling atmospheric disturbances on one frequency, but not in another, and that may be able to tell you what's happening at one height in the ionosphere versus another. So
yeah, what I'm sharing here is one of the Grape stations currently running at 2.5 megahertz. And if I click that, this is a typical fingerprint for the 2.5 megahertz signal. If I go back a couple of days, you can see it varies a bit from day to day, depending on what's going on. But you get a general idea what the fingerprint looks like. And this is for 2.5, where you have a very, very abrupt, this is a good 50 dB drop in signal. If I go here and I look at 5 megahertz, this is the station running now at 5 megahertz. Pop that up, you'll see that it's similar, but this drop off here is much more gradual. And it's very much, during the daytime, you've got that. These are probably really good, because you see the Doppler shift as the as the ionosphere forms a layer and drops the distance, you see the shift up. And then at night, when the thing dissolves, you see the Doppler shift down. So this is a fingerprint of 5 megahertz. And interestingly enough, when I pop up 10 megahertz, which right now I am receiving, this is real time, it's a completely different fingerprint. It's gone during, or there during the night, but gone during the day. It's kind of an inverse. But these are typical plots for 10 megahertz. So even from 2.5 to 5 to 10, the fingerprint of what you see during the day is completely different. And this changes with, well, we have the different storms going on. There are all kinds of different effects due to solar flares, to it just, like I say, it's space science, and that's what the whole intention of this is. And I didn't realize how much was going on and how complicated it was, but there's a lot to be learned here.
Yeah, we go in. I know I certainly went going into many things in life naively, and we learn a lot, right?
You realize how much you don't know. I've
Yeah,
learned a little bit. I don't know a lot about this.
and we continue to learn.
Yes.
I think some of the other questions, well, a couple more things on antennas.
Okay.
Yeah, people keep asking about the antennas for the personal space weather station, and I think the jury's still out on a lot of this. And there's a couple of lines of thought here. Certainly with the personal space weather station, we're saying that any antenna that you can use that's you're able to receive the incoming signal, I think is something that's of value. So, whether you're using an active, a smaller like active magnetic loop or active, receive whip, DX Engineering has a few nice products of that, or using a random wire, or using, something much more elaborate. I think those can all be very helpful. We're also for the Tangerine personal space weather station. We're still evaluating, different. We want to say recommended antennas. We might with the Tangerine. One of the things we might be interested in is getting sampling two different channels simultaneously using orthogonally polarized antennas. So you could measure Faraday rotation in extraordinary and ordinary modes and things like that. And so the exact design for that, hasn't been totally worked out yet. Tom N5 EG is working on a one possible design for an active mag loop. So he's presented that at some of the both TAPR and Hamside telecons in the past. And Zach Lefke, KJ4QLP at Virginia Tech, he's working on a design that he's going to present tomorrow as well. And so I think at the end of the day, we're probably going to have with the personal space weather station, maybe 2 or 3 recommended designs. But one of the things we have to remember with citizen science too is there's only going to be so much control we have over, what people are contributing, because the bottom line is if you set up a personal space weather station as a ham, you have a lot of control over how you want to do the thing, how you want to do this, and what you have access to. So I think there's one of the things that I think we will be doing in the personal space weather station, I know we'll be doing, is we're going to ask people to keep track of what type of antenna they have connected and maybe what its characteristics are. So really the metadata we collect on this project is very important for helping us to understand, what's going on. And hopefully that will lead to good measurements. Let's see. Maybe you can help answer this question. The other question that keeps coming up from people is, when can I buy one? How do I get one of these? What do you want to say to that, John?
Well, so far I've hand assembled all of the great generation 1s. The intent is for generation 2s to have it vendor made.
Yeah.
That's probably going to be coming out, I'm guessing, in the next couple of months. It depends on the GPS DO, if I can get that design working quickly. Or
Yeah.
if I have to talk to John, and I'm not sure where he is at on that. We could revert back to using Leo Bodnar GPS DO initially until that comes out. But that adds $140 to the cost in single quantity. In bigger quantities, we can probably drop the cost down to $110, $120. But still, that's breaking my price point for the low cost station. So,
yeah.
To answer your question, I don't know.
Yeah.
It's basically it's coming, but it's not ready yet.
Right. And I think the way the development is working is, like you said, you showed schematics and drawings for the generation 2, which is what we want to be able to scale up to production quantities. But I think, for people who are asking what's the best way to get involved, it's to go to hamside.org, click the Get Involved tab, go to tangerinesdr.com, get involved. If you participate in the telecons, if you participate in the listservs, that gives you a voice at the table. And
right.
And then we are, like you said, John, he is hand assembling these prototypes right now. And so we really only have like a few small prototypes at the moment. And we start distributing them to core members of the team who've been contributing. And then we also look for certain other, key locations for various reasons, like they're looking for Des Moines, Iowa. All right. It looks like we are getting over to the end of this session, so I'm going to hand it back over to George. Thank you very much, John. Any OB
7 threes from my basement. Take care.
back to net.